Okay, so in this particular video, we're going to look at section 5.3 and 5.4 together, logarithmic functions and their graphs. You will notice in this particular video and from moving forward that I should be able to show you the steps associated with these functions as opposed to just talking through. So hopefully that will be more beneficial for you. All right, so at the top of the set of notes here are basically just properties of exponents that you should already know leading into this class. For example, when you multiply, you add your exponents. When you have a quantity raised to a power, everything in there gets raised to that power. When you raise something to a negative exponent, you just swap places. When you divide exponents, you subtract. When you raise a power to a power, you multiply, things like that. Anything raised to the 0 power is 1. The square root, the nth root of a is a to the 1 over n. The nth root of a to the m is a to the m over n, for example. So I think I talked through basically everything up there. But the reason for that is because these properties of exponents you're going to use extensively as we move through solving logarithmic equations. So I'm actually going to start you here with solving some basic exponential equations, and in doing so you'll be utilizing this property here that it says that if a to the x equals a to the y, then simply x equals y. So essentially what it's saying is if we have the same base on both sides, we can drop those bases and set the exponents equal to one another and solve. All right. So that's going to be our goal down here below in each of these examples, is to try to get the bases to be the exact same. So in example 1, part A here, you have 3 to the negative x and then equals 81. And our goal here is to solve for x. So what we'd want to do is try to figure out then, well, can we raise 3 to a power and get 81? So I'm just going to, we'll have over here, we have 3 to the negative x, and then over here we say, okay, well, 3 to what power equals 81? It happens to be to the 4th power. So now, since our bases are the same, we can drop those bases and set the exponents equal to each other and solve for x. And so at this point, this is a very simple equation, because remember, this is a -1 sitting in front of that x. Just divide both sides by -1. And so therefore, x equals -4. Final answer. And you can always go back and check yourself on these. So for the check here, it would be 3 raised to the negative x, so -4. And you're asking yourself, does that equal 81? And 2 negatives side by side, sure enough, give me a positive, and 3 to the 4th is definitely 81. Okay, so I won't bother checking the rest of them, but I'll let you know that I'm just trying to show you here, you can always check your answers. All right, if we scoot over and look at part B, again, I'm still trying to get these to be the same base. So over here on the left-hand side, I have a 5, and on the right-hand side, I have 1/5. But if you remember up here at the top, well, isn't there another way I can write 1/5? I could write 1/5, when you agree, I could write that as 5 to the -1. And this is still 5 to the x plus 3 over here. And then, let's see if I can go a little smaller on my line. There we go. So now I have the same base. Drop those bases and set the exponents equal to each other. So x plus 3 equals -1, and solve for x. So just subtract 3 from both sides. So x equals -4. It's just coincidence that these two problems happen to both equal -4. Of course, not every exponential equation always equals -4, but that would be our final answer here as well. Okay. Erase a little bit. All right, so I'm going to let you do C. C is very similar to what I've been talking about so far. I'm going to scoot over and I'm going to do letter D here with you. Okay, and if you have trouble doing letter C, then maybe you want to see me do D and then you go back and do C, for example. Okay, but still online in Blackboard, I have the worked out solution key still there, so you have that to check yourself by, because I'm not going to do every single problem in the notes, but I will I'll give you enough information that you should be good to go with that. All right, so here in letter D, you have 9 to the 2x, 27 to the x squared equals 3 to the -1. So hopefully you would agree here, a good base to shoot for then is this 3. So let me get my pen back. Is this 3 here? So I want to try to get everything with a base of 3. So I could write 9 as 3 squared, and that's being raised to the 2x. I could write 27 as 3 cubed, right? Because that's 3 times 3 is 9 times 3 is 27, and that's raised to the x squared equals 3 to the negative 1. Okay. Now, before you just go ahead, you don't drop your bases yet. We got to do some cleanup here. Remember from the exponent rules up top, when you raise a power to a power, you multiply. So this would be the same as 3 to the 4x times 3 to the 3x squared equals 3 to the negative 1. Again, I'm still not ready to drop my bases yet. I need it to be one base equaling the exact same base on the other side. Over here on the left-hand side, I still have 2 bases, so I need to get that down to 1 base. And if you remember, if you have the same base, the rule is when you multiply, you add those exponents. So I'm going to write that as 3x squared plus 4x equals 3 to the negative 1. Now, at this point, I have same bases on both sides. I can drop those bases and set the exponents equal to each other. So 3x squared plus 4x equals negative 1. And my goal is to solve for x. So since hopefully you recall this looks like a quadratic, so I need to get it equal to 0. So I add 1 to both sides. So then I'm left with 3x squared plus 4x plus 1 equals 0. Now from here, we'll try to factor, which I do believe that we can do. So let me get my little eraser here, get rid of that. All right, so now let's go to factor. Go. All right, so the only way to multiply to give you 3x squared, 3x and x, that's the only way. The only way to multiply to give you 1, 1 and 1. So now let's check our outside and inside. So on the outside, 3x times 1 is 3x. On the inside, 1 times x is 1x. My goal is this center term here, which is a 4x. I can get that. I need to make them both positive, so plus plus. And then lastly, I will set both of those terms now equal to 0. So I'll just come up here. So I set 3x plus 1 equal to 0 and solve for x. So subtract 1. 3x equals negative 1 divided by 3. X equals negative 1/3. So that's one answer. And then I set the x plus 1 equal to 0 and solve for x. So just subtract 1 from both sides. And so x equals negative 1. And there's your second answer. So you have 2 possible answers there on that one. Negative 1/3 and negative 1. Okay, so letter E is pretty much the same thing. It's just using that that reoccurring constant, like I showed you in the last video. So instead of essentially, you're going to approach it the exact same way. Instead of having a base of 3, you're just going to now have a base of E in this one. Okay, but I think you should be able to follow what we just did on that one to work letter E there. If you have any questions, always send me an email. I can always work it out for you now and show you step by step and send you a quick video as well. And then, like I said, the solution key that shows all the steps are still there as well. So I think by you hearing and seeing me do letter D over here, that now that'll help you be able to do C and E solo. Okay. All right. So I'm going to scoot on over to the next page. And what do we have there? So at the top of the next page, we've talked about inverses before. Well, it just so happens that the logarithmic function is the inverse of the exponential function. So that will allow us to, what an exponential function is. It's of the form y equals a to the x, or, or any kind of, some base raised to a power. So in order to derive, and instead of me just telling you what the logarithmic function is, I'm going to derive the logarithmic function because, like I said, the inverse of the exponential is the logarithmic function. So let's start with finding that inverse then. And so if you remember back from the first section, to find the inverse, first thing you do, switch x and y. So we would say x equals, let me get this smaller, x equals a to the y. And now our goal is to solve for y. All right, and so I'm going to go ahead and introduce, I can't remember if we've talked about this already. I don't believe we have. No, we haven't. and so this is the reason for logs. When you're trying to solve for the variable that is in the exponent, sometimes you have to take the log of both sides. In our case here, I'm going to take the log of both sides. So I have log of x equals the log of a to the y. The rule is that if whatever is in your exponent can come down in front as a coefficient. So my next step would be log of x equals y log of a. I should mention that it just left me what I was going to say about, oh, I know. Remember, when you find the inverse, you switch x and y, and your goal is to solve for y again. So that's the reason why I have this arrow up here. We're trying to solve for y again, and anyway, we're going to use logarithms to do that. So again, now I want to solve for this y, so I divide both sides by log of a. Whatever you do to one side, do to the other. Log of a. So that cancels out over here. And so then you're left with y equals the log of x divided by the log of a. And technically at that point, you're done. This is what's referred to as the change of base formula. I'll talk more about that on the next page, but also this can be written more simply as the log base a of x. Okay, more to come on that. But essentially, my point in doing what I just did there was to, instead of me just telling you what the logarithmic function was, I kind of wanted to, well, I did. I wanted to show you how you can derive it for yourself, and that comes from just finding the inverse, and the inverse is something we'd already talked about. So the logarithmic function in its most basic form is y equals log base a of x. Couple of stipulations here. Your base a has to be greater than 0, and it cannot equal 1. Okay. The argument here, x, has to be greater than 0. So both the base and the argument both have to be positive, and then we're just saying furthermore that the base cannot equal 1. Okay. Some reasons for that you could go ahead and kind of test for yourself. If you were to try to evaluate in your calculator the log of -100 and trying to figure out what that is, I'm just going to kind of give you a little bit of foreshadowing here. What logarithms do is that they always have some base, and if there isn't a base associated with it, if you have log and you don't have a number down there, it's assumed to be base 10. And so what that means is we're trying to figure out 10 raised to what number equals -100. I mean, that's what we're trying to find. We're trying to find the log of -100. And so if you were to type it in your calculator, here's what your calculator is trying to figure out. It's trying to figure out 10 to what power would equal -100. And hopefully, you know, even without going to your calculator, if you ask yourself, could you ever take a positive number and raise it to a power and get a negative? Absolutely not. Okay, so that can't happen. So that's why we're telling you here that your x value has to be positive. Okay, so that can't happen. So I'm just going to write here, this can't happen. Likewise, the other stipulation, if you have the log of 0, because I said, you know, your log base 10 of 0, you're saying 10 to what power would equal 0? And again, you're not going to be able to do that. You can say 10 to the 0 power, but anything raised to the 0 power is 1. 10 to the first power is 10. 10 squared is 100. If you raise 10 to the -1, you're getting 1/10. So you're not going to be able to do that either. So that also can't happen. So that's why I'm trying to tell you here that your x value here, your argument, has to be greater than 0. It has to be positive, and it cannot even equal 0. So, all right. So just below that, I have us graphing an exponential and a logarithmic function. So what I want us to graph is I want us to graph y equals 10 to the x versus its logarithmic function, y equals log of x. So if we do that, draw a little coordinate plane. I would just say, at this point, you just sort of consult your calculator. I am going to, these are supposed to be inverses of one another, so they should be reflections across the line, y equals y equals x, right? And we talked about that in that first section. So they should be a reflection across that. And so sure enough, if you were to put in your calculator y equals 10 to the x, you would be getting this function. Looks something like that. And I'll label it for you. This is y equals 10 to the x. That's the exponential function. Then if you were to go and graph the logarithmic function, y equals log of x. So you could put 10 to the x in y1 and log of the x in y2, and you would see something like this. And this would be y equals log of x. And so sure enough, they are definitely a reflection across the line y equals x. Okay. So I'll scoot on down from here. A couple of facts. A logarithm, so when I say logarithm, we're just talking about here your common log. If it does not have a base written, it's referred to as, like I said, the common log, and it's assumed to be base 10. I'll be pointing that out along the way. A natural log is base e. It's that common reoccurrent constant like we talked about in the last section, and it is referred to as ln or ln, either way, either your capital L or the lowercase. And you have both of these buttons in your calculator. All right, so if we scoot on down then to example 2, this is what I mean right here. I'll just go ahead and talk about this. It says log base 5 of x. So because it has a base 5 down here, then it's common log, but it is not considered to be base 10 because it actually has a number sitting down here. Okay, so that's what I was referring to a minute ago, that if it doesn't have a number sitting down there, then it is referred to as base 10. If the number is sitting there, then it's whatever this number is. So with that said, these particular examples here want us to convert from logarithmic to exponential form. And so in order to do that, it is just a very simple technique. It's the base raised to the opposite side, so 5 squared equals x. That's essentially what that logarithm is trying to compute, that it's trying to figure out 5 to the second power equals x. And so of course we know that that would be 25, but this is all that I want you to do is just go from logarithmic to exponential form. And so the 5 squared equals x is your exponential form. Now we could solve it. I'm going to go ahead and do that just so that you kind of get an idea here. So, of course, then we would know that x equals 25. And so then really what it's saying then is log base 5 of 25 equals 2. Because, and we know this. We essentially, if we didn't know this part over here, if we just had log base 5 of 25, then we would be asking ourselves 5 to what power equals 25? That's what logarithms do. They tell you a base raised to what power equals this argument. And so, okay, well, we know that. That's x equals 2. 5 squared equals that. Okay, just trying to give you a little bit of background as far as we know what are these logarithms mean. All right, so I'll erase that for us, because all we need there is that part in blue. So if we scoot on over then to the next example, again, we're just going to write this in exponential form. Base raised to the opposite side equals the argument. So b cubed equals 64. Probably a good idea for you to pause and do letter C there. And we'll scoot on down to example 3. And check, like I said, and check yourself by the answer key online in Blackboard. Example 3, we're just going opposite here. I'm giving it to you in exponential form, and now we want to go to logarithmic. I always find this way a little harder, and so whenever I do it, I always check myself by going backwards. So, but 12 cubed equals x, so it's log base 12 of x equals 3. Because remember, it's base raised to the opposite side equals argument. Okay, so this right here is final answer. One more. Log base b of 8 equals 3. And so you could check yourself. Okay, base raised to the opposite side, b cubed equals argument there 8. Okay, final answer. We will need these properties in order to solve logarithmic equations moving forward. So, you know, it's just kind of, we're not just doing it for converting purposes, there will be a purpose for them moving forward. Okay, so down in example 4, it says use the definition of logs to find each logarithm. So, like I was saying, that definition of logs is meaning then log base 2 of 8, this says, essentially it's like an x over here, equals what? Okay, so you're saying 2 to what power equals 8? And that should be something you should be able to eyeball, but if not, then you could think of it as, okay, let me get this to the same base like we were doing on the front page. Or I could write 8 as 2 cubed, drop the bases, x equals 3. You don't have to go all that way. I mean, you can look at it right there and say, oh, 2 cubed equals 8. Well, I'll let you try letter B. I'm going to scoot over to letter C. So this says log of 100. So remember, if it doesn't have a base, it's assumed to be, since it's log, it's assumed to be base 10. This equals x. So I'm trying to say here, 10 to the what power equals 100. And so, okay, I know that. That's x equals 2, right? Because 10 squared would equal 100. Now, I will say, because in letter C here, this was base 10, you could type that in your calculator. And if you typed in log of 100, your calculator's going to spit right out at you, x equals 2. At the moment, you don't know how to do letter A in your calculator, but I'll show you that in just a moment. All right, scoot on over to D. D says it wants you to calculate the natural log of E. So we're trying to figure out what that is. Remember from one of the facts above, natural log is already, if it's not written there, and it does, actually natural log is always base e. So here we're saying e to the what power equals e, and essentially this is like e to the first power. So bases are the same, drop them, x equals 1. Okay, so natural log is always base e, so e to what power equals this argument here, which is just e, and so I just put a 1 up there on that exponent so that you could see, oh, okay, well they have, anytime you have the same base, drop those bases, set the exponents equal one another, and solve. And here you're already solved, okay? Now in example 5, you're just throwing these in your calculator, so it would be as simple as type in your calculator ln pi, log 100. Log 25, and so on. And I've got you, well, it looks like on my solution key I rounded it to 2 decimal places. So I'm going to let you try that, and let me know if you need any calculator help, okay? I'm going to scoot on over to the next page. All right, so at the top of the next page, I talk about that change of base formula, and actually you've already seen the change of base formula whenever I was doing the derivation of the logarithmic function just a minute ago. So what that says is that the change of base formula allows us to find logarithms that are in our calculator that are beyond base 10. So your calculator can do log base 10, but it can't do others. So if you have log base a of some argument, then it's equal to the log of the argument divided by the log of the base. And it's also legal if you don't want to use common log, you can use natural log. Natural log of the argument divided by natural log of the base. So it is not it doesn't matter which one you use, okay? Example 6, there's just a stray log sitting there. I need to delete that. So scooting on down to example 6, it says use the change of base formula to solve for each logarithm. Now the first one, I chose it because I wanted you to be able, this is one we could do without using the change of base formula. So let's first do it without using change of base formula. So we would be saying here 3 to the what power equals 9. And hopefully you can eyeball that. Oh, that would have to be 2, right? Because 3 squared would equal 9. Well, the change of base formula says, okay, well, since this is not base 10, we wouldn't be able to just type this in our calculator. What we can do then is we can, in our calculator, say the log of 9 divided by the log of 3. So the log of the argument divided by the log of the base. And let me pull my calculator real quick and make sure, parentheses are important. So yeah, so like log automatically opens up a parenthesis, be sure you close it, then divided by log of the 3 on the bottom. And it'll give you that perfect too. Just so you know, you could also use natural log here. Natural log of 9 divided by natural log of 3. Same thing with natural log. It automatically pulls up a parenthesis, so be sure you close it. So natural log of 9 divided by natural log of 3. And you'll get 2. So you can use common log or natural log whenever you're doing your change of base formula. We'll do one more together. So B and C, there's, like for example, in part B, you'd be saying 2 to the what power equals 7. Well, 2 squared is 4, 2 cubed is 8. So it's somewhere between 2 and 3. We just don't know exactly what value that is. And we can, instead of doing like this trial and error with it, we can just say simply log of the argument divided by log of the base. Or natural log of the argument divided by natural log of the base. Either way you do it, you're going to arrive at 2.81. I just did 2 decimal places throughout this whole set of notes. Okay, and I'll let you try letter C there, and I've shown my work on the solution key. All right, so if we scoot on down, then you see a couple more properties that we'll pick up. The first one says log base b of 1 equals 0. So that's just saying, remember, that's, if you were to think about it, that's just saying b to the 0 power equals 1. Anything raised to the 0 power equals 1. So that's why anytime you take the log of whatever your base is of 1, it's always equal to 0. The next one down, log base b of b equals 1. So that's just saying that when your base and your argument are the same, then your answer is the exponent up here, which in that case is 1. If you scoot on down to the next one, your base and your argument are the same, so that cancels out, and it just leaves you with whatever's your exponent. So if your exponent's x, then your answer is x. If your exponent's 4x squared, then your answer is 4x squared. This next one may not look like, I don't feel like it kind of translates how I want it to look. I want it to look like this, that you have b raised to log base b of x. Okay, so all log base b of x is all in the exponent there. And so again, when your base and the base here both match up, then your answer is whatever is here for that argument. So that's what you're seeing there. Same rules apply for natural logs. Natural log of 1 is 0. Natural log of e is 1, because remember this is base e. So answer then will just be the exponent. Again, this is natural log base e, so answer is just the exponent, x. Now e raised to the natural log of x, so that is base e, so these match up. The answer is just that argument there, which is x. Okay, so let's scoot on down then, and let's look at example 7. It's an application, but in the previous section when we did an application, we didn't have logarithms to be able to solve exactly, so we had to rely on our calculator intersection feature. Well, now we'll be able to utilize the logarithm functions to solve it. So they tell us that the risk of having a car accident when drinking and driving is given by this formula, R equals e to the kx, where x represents the percent of your blood alcohol concentration in the body and k is a constant. So in part A, they say, well, if the risk is 1.4 for a blood alcohol concentration of 0.02%, find k. So I'm using my formula here that R equals e to the kx, plug in what I know. So I know my R risk is 1.4 equals e to the k, we don't know, and x is the blood alcohol concentration of 0.02. You don't need to change that to a decimal because it's telling you that your k, your x here, x is a percent. Okay, so keep it in the percent format. I'm going to just rewrite that then as 1.4 equals e to the 0.02k, like so. Now our goal is to solve for k. So we think about, okay, well, how can I get k out of the exponent? Since it's e is raised to that power, you think about, well, is it better to take the log or the natural log? And hopefully you would agree that if I took the natural log of both sides, let me erase that. If I took the natural log of both sides, natural log here, that natural log of 1.4 is just going to be some number, so I'm just going to leave that, natural log of 1.4. But over here on the right-hand side, this is natural log already base e of e. They cancel out, and it just leaves me with what's here in the exponent, the 0.02k. So again, anytime you have e raised to a power and you're trying to solve for something in the exponent, take the natural log of both sides. And so now to solve for k, just divide by 0.02. Cancels out. And so in your calculator, you'd be putting in natural log of 1.4, close parentheses, divided by 0.02. And that should arrive you at approximately 16.82. Second, try that. Now from there, and you know, sometimes if I don't give you enough time, just pause so that you can have enough time, and I don't prolong the video and stuff like that. Okay, so in part B it says, well, let's now find the risk for a 0.17% blood alcohol concentration. So now we're thinking about our formula here. Then we have R equals E. We now know what our K value is. 16.82 times our X percentage, and they just told us that that is 0.17. So you would just type that directly in your calculator, E raised to the 16.82 times 0.17, and you should get a risk there of 17.5. So a person will be 17.5 times more likely to have an accident with a 0.17 blood alcohol concentration. All right, and then if we scroll down then to, so I'll just kind of write that basically times more likely. 17.5 times more likely to have accident. All right, so we'll scoot on down then to part C. So it says if your risk is 4 or more, then you would be given a DUI. So they want us to find the blood alcohol concentration for this particular risk. We should expect it to be 0.08, right? Because that's the legal limit. So it should be essentially at that or higher, right? Because it says if it's 4 or more. So we would set here my risk 4 equal to my E to the 16.82x, because I'm trying to figure out what the blood alcohol concentration is. Since I want to solve for a variable that's in the exponent, I need to get rid of this E down here, just like before. Take the natural log of both sides. So I have the natural log of 4 equals the natural log of E to the 16.82x. On the right hand side, then this is base, natural log is base E. When the base and the argument there match up, then the answer is just what's in the exponent. So the natural log of 4 equals 16.82x. Divide by that 16.82. Cancels out, and so x equals, when you put that in your calculator, you should get x equals 0.082. So basically that's your 0.08%. You're essentially above 0.08 at that point, which is, like we said, above the legal limit. All right, so we move on down to example 8. It says find these logarithms without using a calculator. Essentially, you're using these properties that I've been showing you. So you're thinking about, okay, now common log is base 10, natural log is base E. Those other properties that I just showed you up at, just before that application problem that we just did. So I'm just going to do a couple of these with you. So like, for example, in letter A there, the log of 10, remember, since it's common log there, then it is considered to be base 10. So we're saying 10 to the what power equals 10. And so hopefully you agree here, oh, x equals 1. Or technically in this problem, I didn't have to do that, right? Because this is base and argument match up, so answer's got to be exponent up there. So x equals 1. Use that same technique on letter B here. Natural log of E. Sure, you could put it in your calculator, but also natural log is base E. So base and argument match up, so answer is just the exponent. Imaginary 1 sitting up there, so also 1. Letter C. Log of base 3 of 3. So these cancel out, just leave you with the exponent. Imaginary 1 sitting up there, so answer is just 1. The last one, natural log of 1. So remember, this is base E. We're saying E to what power equals 1. What number you can raise E to what power and always get 1? E raised to the 0 power. Anything raised to the 0 power is always equal to 1. So x equals 0 there. That would be something, though, you could type in your calculator. Natural log of 1. It would tell you it was 0. I'm going to scoot on down. Let's do letter H together. E raised to the natural log of 2x. You can think of this as E raised to the natural log. Imaginary base down there on that natural log is E. So when the base and these two bases match up, answer is just this argument here, 2x. Final answer. And then lastly, in letter I, Just might be something you might not think about. 0.01. What's another way you could write that? 0.01. If you said that out loud, that would be read as 1/100th or 1/100ths. So 1/100. Well, I could think of that then as, okay, well, that's the same as 1/10 squared. That's the same as 10 to the negative 2. Right? And that's one of the properties that you saw on the front page. Common log is already base 10, so when the base and the argument match up, answer is just the exponent, so you would have negative 2. Again, since this was already common log, you could have typed in log of 0.01 and your calculator would have given you negative 2 straight away. Okay, is there next page? Yeah. All right, we'll flip on over to the next page. Properties for expanding and condensing logs. Again, something that'll be useful for us as we move into the next section for solving logarithmic equations. So you have the product rule, and these rules here are very similar to the rules for exponents. So the product rule, it says log base b of x times y. Remember, when you multiply, you add your exponents. So when you multiply arguments there, you can just break it up into to the addition of those two arguments. So log base b of x plus log base b of y. The division of an argument turns into subtraction. So multiplication turns into addition, when you think about it. And when you have a power of x to the n, I showed you this technique a minute ago when we were solving, the power comes down in front as a coefficient. Okay, so when you multiply, you add your exponents, so same thing you do with logs. When you divide, you subtract your exponents, so same thing you do with logs. And then the power rule is the only thing different. The power comes down in front as a coefficient. Okay, so in example 9, you're expressing each as a sum or difference of logs. Okay, so erase that and let's get into that first one. I think what I'll do is I'm going to do number 7 and number 9 with you. All right, in number 7, you have log base 3 of x times the square root of x plus 1. So let's first, before I try to start breaking this up, let's think of the square root. The square root is the same as what power? Log base 3 of x times x squared plus 1 raised to the 1/2 power. Now from there, we know this is multiplication, so multiplication turns into addition. Break this up. Log base 3 of x plus log base 3 of x squared plus 1 to the 1/2. So far so good. All right, so the next piece is, my only last piece is I have a power, and that power needs to come down in front as a coefficient. So final answer, log base 3 of x plus 1/2 log base 3 of x squared plus 1. This argument back here, sometimes folks want to try to go further with it. It's an addition, so you can only take multiplication division further. So addition and subtraction of an argument you can't take further. So this would be our final answer there. Okay, and I'll let you try example 8. I'd like to do example 9 with you because there's a lot going on in that one. Okay, so in example 9, you have log base a of the square root divided by 2 pieces, x cubed times the x plus 1 to the 4th. So first thing I'm going to do is let's think about that top. Remember, just from like that previous example that we were just looking at, well, I could really think of this as x squared plus 1 to the 1/2. So I've got division here, so I can turn division into subtraction. So I think of this as log base a of x squared plus 1 to the 1/2 minus log base a of x cubed times x plus 1 all raised to the 4th. Okay, now from here, we've got a couple of moves. I think what I'll do first is I'm going to take care of this back end back here where you have the multiplication. You've got x cubed times that, so I can change that multiplication into addition. So I have log base a of the x squared plus 1. you know, there's a lot of different steps you can do here. Just eventually at the end, you get the same as I do. Okay, so then minus, you're going to notice here how I'm going to use a parenthesis at this point. I'll talk about that in just a second. Log base a of x cubed, it's multiplication, so it turns into addition. Log base a of x plus 1 to the fourth. I put that minus sign in front of that whole piece there because if you remember, this entire piece here has to be in the denominator. And so if you don't have the parentheses, then you're not going, if you think about working backwards, then it's not going to put both of those pieces in the denominator. So I'm going to need, my next step would be to distribute that negative through that parenthesis so that I have log base a of x squared plus 1 to the 1/2 minus log base a of x cubed minus log base a of x plus 1 to the fourth. That way you have this first term, x squared plus 1 to the 1/2, minus tells me to divide by x cubed and also divide by the x plus 1 to the fourth. I've got one more step, and that is to pull all of those powers down as coefficients in front. So it will look like this. 1/2 log base a of x squared plus 1 minus, pull that 3 down in front, 3 log base a of x minus 4 log base a of x plus 1. And that will do it. That's your final answer. Okay, so that one had a lot going on in it. I just wanted to just draw your attention to utilizing the parentheses there so that you put, if you were to work backwards now, you could get the original problem right back. Okay. All right, so if we scoot on down then to example 10, in example 10 we're going to express this as a single log. And so essentially you're working backwards. So coefficients in front come up as exponents, subtraction tells us to divide, addition tells us to multiply. Okay, so with that said, I think I'll do 10 and 11 with you and let you try 12. So in number 10 I have this, number 10 I have this 5 in front, so I'm going to bring it up as an exponent. I have this 1/3 in front, so I'm going to bring it up as an exponent, so that would be my first step. So I have log of x to the 5th minus log of y plus log of z to the 1/3. Okay, now I have everything is a common log, so I can write this now as one log, a single logarithm. I start with my x to the 5th. It tells me to divide, because minus log, it tells me to divide by y. And then it tells me to multiply it times z to the 1/3. So that means then I'm going to put my z to the 1/3 up top. And that would be my final answer. Really like the log of that whole piece there. That would be my final answer. All right, and if we move over to example 11, you have natural log of 66 minus natural log of 6. So essentially at that point you don't have any coefficients, so I can write 1 natural log. Subtraction tells me to divide, so 66 divided by 6. In this particular case, these are values, so we could go ahead and reduce that. That would be the natural log of 11. Final answer. You know, and since this is all numerical values in this particular problem, if you were to go at the very beginning and type natural log of 66 minus natural log of 6 in your calculator, you would get the exact same value if you were to just simply type the natural log of 11. Or if you were to type this piece right here, you would all get the same value, but reduced final form single log would be your final answer here, natural log of 11. Okay, I encourage you to try example 12. Like I said, it's answers on the solution key. And then lastly here in example 11, they're giving you some information about a particular log, but they're not telling you what the base is. So you would have to use the information given. You couldn't just find it on your own, for example. So they're telling us log base b of 2 is this value, log base b of 5, and log base b of 7 are those values. They want us to find log base b of 7/10. Okay, so let's try to, you know, kind of work backwards so that we can try to utilize, so we can get down to bases here or arguments of 2, 5, and 7. If we can get it down to those arguments, then we have values to work with. So division here tells us that we can expand that into subtraction. So log base b of 7 minus log base b of 10. Now from there, I have the 7, I have got that one, but I don't have anything for 10. Well, hopefully you would agree that, well, is there a way I could write 10 utilizing these arguments that I have, 2, 5, and 7? Hopefully you would agree that I could write that as log base b of 2 times 5, because 2 times 5 is the same as 10. Now with that said, sort of clean that up a little bit further. So log base b of 7 minus log base b of, I'm going to do like I did before since it's multiplication there and I got a minus sign in front. So it would be log base b of 2, multiplication tells me to add, log base b of 5. Now I'm going to take that minus sign and distribute it through. So I have log base b of 7, log base b of 2 minus log base b of 5. And then all of these values are given to you. Log base b of 7, that's the 0.901, minus 0.352, minus 0.789. And if you were to put all of that in your calculator, you would arrive at a negative 0.24. Okay, so that's the idea there. I hope this helps. Let me know if you have any questions. Thanks a lot. Bye.